Let us take a look at the transformation of derivative. Can we drive a formula out of it? First of all, assume f, first derivative, second derivative, until n-1 derivative of f. They are all continuous on the interval 0 to infinity, and 0 is included. And they are of exponential order. And if the nth derivative of f is piecewise continuous on 0 to infinity, then the Laplace transformation of the nth derivative of f can be written as s to power n times f of s minus s to power n minus 1 times f of 0 minus s to power n minus 2 f prime of 0. You can continue this process minus the nth minus 1 derivative of f at 0. F of s is nothing but the Laplace of f. For example, suppose f prime is continuous for positive values of t including 0, then integration by parts gives us the Laplace of f prime of t, which is the improper integral of e to power negative st. And remember that wherever we see the function, we're going to substitute that by f prime. By using the integration by parts, as you remember, you have the integral of u dv, which is uv minus integral v du. We can write this guy as e to power negative st times f of t. T ranges between 0 to infinity, plus s times the improper integral 0 to infinity of e to power negative st f of t dt. We can do the computation here and simplify this as well. The Laplace of f prime of t can be written as negative f of 0, because when you plug in infinity, this term vanishes, and you end up with negative f of 0 plus s times, but this integral is the definition of Laplace of f of t. So you can say that, hey, the Laplace of f prime of t is nothing but s times f of s. Again, f of s is represented by the Laplace of f of t minus f of 0. With the same argument, we can write down the Laplace of second derivative of f, which is s squared f of s minus s times f of 0 minus f prime of 0. But why this is useful? How are we going to use these? We're going to use these and basically solve a differential equation using the Laplace and the inverse of Laplace. Let's take a look at one example together. So far, we saw that the Laplace of f prime of t can be written as s of Laplace of f minus f of 0. So for simplicity, we're going to use f of s or any other function of this sort. We're going to use the Laplace transformation to solve the initial value problem given as y prime plus 3y equals to 13 sine of 2t, and it has initial value. When t is equal to 0, your y is 6. Let's take a look at the solution. First, we're going to take the transformation of each member of the differential equation. The transformation of the first derivative plus 3 times the transformation of y. On the right-hand side, you have 13 times the transformation of sine of 2t. So one by one, term by term, we take the Laplace transformation of each one of these. Remember that the Laplace transformation of y prime is s times f of s. F of s can be represented by capital Y, because here you have your function like y. So let us use y of s instead of f of s. Both of them result in the same thing. But for simplicity, let's use y of s minus f of 0 that can be represented by y of 0. Remember that y at 0 is equal to 6. So if you substitute it here, you get minus 6. So far, we calculated the Laplace of y prime. Now, let us calculate the Laplace of sine 2t This is, as you remember, is 2 divided by s squared plus 4. Now, on the left-hand side, we're going to substitute for the Laplace of y prime, which is s times y of s minus 6, 3 times Laplace of y, which is 3 times y of s. And on the right-hand side, you have 13 times 2 divided by s squared plus 4. So let us do the algebra now. S times y of s plus 3y of s is equal to 6 plus 26 over s squared plus 4. Our goal is to isolate y of s on one side and solve it. If you factor out y of s, you get s plus 3 times y of s equals to 6 plus 26 divided by s squared plus 4. So let us go to the next slide and continue the process. So far we saw that s plus 3 times y of s is equal to 6 plus 26 divided by s squared plus 4. So y of x can be written as 6 divided by s plus 3 plus 26 divided by s squared plus 4 multiplied by s plus 3. So if you take common denominator, you get 6s squared plus 50, and this is your common denominator. We can use partial fractions and break this fraction into two simpler fractions. You have a divided by s plus 3 plus bs plus c divided by s squared plus 4. By using the method of partial fractions, we're going to find these missing values. 6s squared plus 50 must be equals to a times s squared plus 4 plus s plus 3 times bs plus c. You can set s to be -3 to get rid of the quantity on the right-hand side, and substituting -3 gives you a times 9 plus 4, which is 13. And on the right-hand side, if you plug in -3, you get 6 times 9 plus 50. When you do the division, a becomes 8. So 6 is equal to a plus b, and 3b plus c is equal to 0. If you plug in a equals to 8, b can be calculated as -2. Since you have b, you can easily calculate c. C is equal to 6. So we have all the missing values. Y of s is equal to 6 s squared plus 50 divided by s plus 3 times s squared plus 4. That can be written as 8 divided by s plus 3 plus -2s plus 6 divided by s squared plus 4. Now we can work this out and find the Laplace transformation using the inverse Laplace. We can see that y of t is equal to 8 times the inverse Laplace of 1 divided by s plus 3. And we can separate this fraction into two fractions as well. -2 inverse Laplace of s divided by s squared plus 4 plus, here you have 3 times inverse Laplace of 2 divided by s squared plus 4. Remember that we keep 1, 2 on the numerator because you have 4 down here. So from what we learned before, inverse Laplace of 1 divided by s plus 3 gives you e to power -3t. The inverse Laplace of s divided by s squared plus 4 gives you cosine 2t, and the inverse Laplace of 2 divided by s squared plus 4 gives you sine 2t. Don't forget to put the coefficients here, and this is the solution of this differential equation that we try to solve. So that's the application of Laplace transformation and inverse Laplace transformation in solving first-order differential equations. Let us take a look at the second-order differential equations. Suppose I ask you to solve the following differential equations. The second derivative of y minus 3y prime plus 2y is equal to e to the power negative 40. Y at 0 is 1, and when your independent variable is 0, the first derivative is 5. Let us begin. What are we going to do? We're going to take the Laplace of each one of these terms. You have the Laplace of the second derivative minus 3 times the Laplace of the first derivative plus 2 times the Laplace of y equals to Laplace of e to the power negative 40. Remember the formula. The Laplace of first derivative is s f of s, that you can use y of s instead, minus f of 0. And the Laplace of the second derivative is s squared f of s minus s f of 0 minus f prime at 0. So we're going to substitute these, use algebra, and then partial fractions to solve this differential equation. So first of all, the Laplace of the second derivative is s squared y of s minus sy0 minus y prime at 0, which is the same as the formula that we have here. Minus 3 times the Laplace of y prime is s y of s minus y at 0. This is basically following the formula that we introduced. Plus 2 times Laplace of y, which is nothing but y. And on the right-hand side, you have Laplace of e to the power negative 40, which is 1 divided by s plus 4. Very good. So let us do the algebra and simplify this as much as we can. By doing the algebra, we're basically distributing negative 3 into parentheses and then factoring out y of s. You end up with s squared minus 3s plus 2 times y of s, and on the right-hand side, you have 1 divided by s plus 4 plus s plus 2. Now what are we going to do? We're going to do a little bit of division. Y of s on the left side is s divided by s squared minus 3s plus 2, 2 divided by s squared minus 3s plus 2, plus 1 divided by s squared minus 3s plus 2 times s plus 4. Very good. So now we have this summation of two fractions. Let us take the least common denominator and simplify the numerator. We end up with s squared plus 6s plus 9. And the denominator, you have s minus 1 times s minus 2 times s plus 4. Let us move to the next slide. Y of s, as we saw, is s squared plus 6s plus 9 divided by the multiplication of these three distinct linear terms. We're going to use the method of partial fractions to break this guy down into smaller fractions. This can be written as the unknown a divided by s minus 1 plus unknown b divided by s minus 2 plus unknown c divided by s plus 4. So our goal is to find a, b, and c, and finally apply the formula that we learned here. To do that, we're going to take the common denominator between these three fractions. On the numerator, you end up with a times s minus 2 times s plus 4 plus b times s minus 1 times s plus 4 plus c times s minus 1 times s minus 2. And the denominator is going to be just the multiplication of these three linear terms. So as you can see, since the denominators are the same, the numerators must be the same as well. So s squared plus 6s plus 9 on the left must be equal to the numerator on the right. We're going to use some shortcuts to find a, b, and c. So this is what we have so far. We're going to set s equals to 2, s equals to 1, and s equals to negative 4 to calculate a, b, and c. So if s is equal to 1, basically these quantities, they all disappear. and you end up with 1 plus 6 plus 9, which is 16, equals to a times negative 1 times 5. We're going to do the same thing, plug in s equals to 2 to calculate b, and plus s equals to negative 4 to calculate c. That helps us to break down our complicated fraction into smaller pieces. So remember that s squared plus 6s plus 9 was a divided by s minus 1 plus b divided by s minus 2 plus c divided by s plus 4, and this was our denominator. So our fraction on the left can be written as negative 16 divided by 5 over s minus 1 plus our b is 25 over 6. So you get 25 over 6 divided by s minus 2 plus c, which is 1 over 30, divided by s plus 4. So our y of t, which is the inverse Laplace, you're going to take the inverse Laplace of each one of these quantities. The inverse Laplace of negative 16 over 5 of s minus 1 is negative 16 over 5 of e to power t. The inverse Laplace of 25 over 6 divided by s minus 2 is 25 over 6 times e to power 2t, and 1 over 30 inverse Laplace of 1 divided by s plus 4, which is e to power negative 40. So this is the solution of the differential equation that we tried to solve using Laplace method.